Monday, this is the 26th of April. You guys will be able to define and identify trapezoids, isosceles trapezoids, kites, and find their measures, section 8.5. Wednesday, my dudes, will be reviewing for our test, which means on Friday, Fun Sock Friday, we'll be taking our Chapter 8 test, okay? There will be math testing the following week, okay? The following Tuesday, Trooper Tide Tuesday. We're going to finish off these note cards, so we're doing trapezoid. Now, once again, you guys did have that day in class where I was not here to do that GeoGebra activity and to go through and start filling out these note cards. So I'm going to assume that you worked on that like you should have and continue at a pretty decent pace today with these note cards, okay? So that means if you didn't and you missed something, I'm going to request that you go back and get these later, which on this video that I will post. Does that make sense? Is that understood? Alrighty. So, trapezoid note card. What else is it? Nothing. It's literally no other special quadrilateral. It is just a quadrilateral. It's not a parallelogram, not a square, rectangle, or...
What does the trapezoid look like?
A trapezoid looks like that.
Okay.
So, trapezoid is nothing else. The lengths, there is no relationship. There is nothing special with the lengths of a trapezoid, of any of the sides. Not quite. A little bit. Okay? Slopes. There are one pair of opposite sides that are parallel. Exactly one pair. How many pairs did parallelograms have? Two pairs, right? Both pairs, okay? Trapezoid, just one pair of opposite sides are parallel. The angles, two pairs of consecutive angles are supplementary. Now notice with a parallelogram, all pairs of consecutive angles are supplementary. Is that the case here? No. Two pairs of consecutive angles are supplementary. And I'll show you which two pairs in a moment, okay? So on this trapezoid, here's a picture of one. Notice there's one pair of parallel sides. The pair of parallel sides is called a base. They're both bases, so there's two bases. Typically, you'll see them drawn to where the base is on the top and the bottom like this. It will not always be the case, though. It can be rotated any sort of way. It's just like we can rotate a triangle by kicking over the stool in this class. Okay? Same idea.
Do it again.
So whatever the parallel sides are, though, those will always be the base. The other ones connecting the bases together are called the legs. So you have two bases and two legs in a trapezoid. In any trapezoid, that'll be the case. Now, when we say that there's one pair there's two pairs of consecutive angles that are supplementary, meaning two pairs of consecutive angles added to 180. It's going to be the two angles connected to the legs. So, in this case, it's going to be this angle and this angle. I will call them the leg angles. Does anyone know why I'd call them leg angles? Because they're two angles touching the same leg. Now, granted, they're both touching bases, but are they touching the same base? No. But are they touching the same leg? Yeah, so I will say the leg angles are supplementary. That might not be a bad thing to write in on your note card there. In parentheses, leg angles. So two pairs of consecutive angles are supplementary. Put in parentheses maybe leg angles, okay? That means over on the other side, we also have another pair of leg angles. The two angles touching this side, this leg. Those two angles are supplementary to each other, as well as these other two. But we don't know anything about congruent angles, okay, in a trapezoid. In a regular trapezoid, there is nothing special about the angle measures besides this fact. No congruent angles. Does that make sense? Okay. Continuing on. Diagonals, nothing. Is there much we can really write down about a trapezoid? No. We also have our definition. It is a quadrilateral with exactly one pair of parallel sides. And that's really about all we know about it anyway, right? Besides the leg angles are supplementary. Yeah. Just the one pair of parallel sides and exactly one pair of parallel sides. Continuing on to some examples, actually, to work on this. So, what kind of shape is this?
Trapezoid.
Trapezoid. How do we know? Besides, we just talked about it. Seth, you said?
Because all sides are not congruent.
Okay. Well,
And the
yep.
angles are not congruent.
This is in our note packet. We're doing note packet right now. We're kind of going back and forth today, okay?
Angles are not congruent.
How many pairs of parallel sides? One pair. That's how we know it's a trapezoid. That's how we know. That's the identifier for a trapezoid. One pair of parallel sides, trapezoid. Instantly know. Now, what do we know about finding x and y here? How could we find x? Landon.
You said x plus 48 plus 103 equals 80.
Not quite. I'm going to disagree on that. X plus 48 plus something will equal 180, but I don't think it's 103. Okay? Seth, what do you think it would be? Plus 65. Elizabeth, why would it be plus 65?
Oh, I understand why.
Okay. Do you want to tap in, Bailey, then?
Because they're on like the same like leg angle.
Very good, because they're a pair of leg angles. Way to even use the vocab I chimed in there. I liked it. Okay? They're a pair of leg angles. They're two angles touching the same leg. We can call them langles as a slang if you really want to, I suppose. Okay? So you can add those two angles equal to 180 degrees. We can combine x plus 48 plus 65 is 113. Disagree. Equals 180. Subtract 113. And x is 67. Does that mean this whole angle B is 67? No, you'd have to add it back with 48. But x is 67. Okay? Raise your hand if you can help me find y. Bailey, go ahead.
Y plus 103 equals 180.
Very good. And why does that work, Seth?
Because that's all that we have. That's all the angles we have on that leg.
Okay, so it's both leg angles then. Is that what you're trying to say? Okay. Yep, both pairs of both of the leg angles for that leg. So the pair of leg angles. So they're going to be supplementary. Subtract 103. Thank you for being willing to help out with that one, Elizabeth, as well. And y is 77. Questions on that?
Why are there no congruent angles?
That's the point.
Alrighty. Let's talk about an isosceles trapezoid. So our next note card. Back to our note card, isosceles trapezoid. Well,
I get that one on the back.
ooh, there you go.
Should we do this here?
Not yet.
Okay.
Yep. We're going to pause on the note packet, go back to the, we're going to go back to it in a bit. Yep. Definition. A trapezoid with congruent legs.
Yeah, you did it.
So are the bases congruent?
Maybe. No.
No. The legs are. The legs are.
Freaking leg.
If the bases were congruent, it actually wouldn't be a trapezoid. It'd be a parallelogram.
Rectangle.
But not necessarily. So trapezoid with congruent legs. Now, does that make sense? When we called something isosceles before, what happened with the isosceles triangle?
They got two sides.
Two sides were congruent, right? Well, how many sides are going to be congruent in an isosceles trapezoid? 2. So does that kind of follow suit there? Can we use that prior knowledge to help us remember this? Yeah, I think so. Okay. So what else is it? Well, it's a trapezoid. I mean, that's kind of in the name, isn't it? Okay. The sides, one pair of opposite sides are congruent. Now, which sides are those? The legs. Might not be a bad idea to write that in. The legs. The slopes tell us, once again, that one pair of opposite sides are parallel. Exactly one pair of opposite sides are parallel. Now, what sides are parallel here?
Leg.
Nope.
Bases.
The bases are parallel. The bases are parallel. Remember, the legs connect the bases. Okay? Okay, relationship of angles. Two pairs of congruent base angles, as well as two pairs of supplementary leg angles. So is the leg angles part new? No, we saw that in trapezoid, which it also is. What part of this is new?
The beginning.
The beginning, the two pairs of congruent base angles. Now wait, what do you think are going to be called base angles?
The ones that are parallel.
Okay, the bases are the ones that are the sides that are parallel. What are we going to call base angles compared to what we called leg angles? Okay, they're congruent, but how are we going to identify what's what? The leg angles were angles touching the same leg, correct? So what would a pair of base angles be doing? Touching what?
The base.
The same base. Pair of base angles will touch the same base. So two angles touching the same base in an isosceles trapezoid are congruent to each other. If a trapezoid, back to the theorem real quick, and we'll hop back to the note card. If a trapezoid has a pair of congruent base angles, so we're saying, okay, we know that angles D and C are congruent. Okay? Because would we say that side AB and side DC are going to be the parallel sides here? Yeah, so those would be the bases. Would angles D and C be a pair of base angles? Yeah, because they're two angles touching the same base at the bottom there. If we know that those angles are congruent, then it's an isosceles trapezoid. You guys remember how with a parallelogram, there are more ways to identify as a parallelogram than just if the sides are parallel to each other, right? We could say, hey, if both pairs of opposite sides are congruent, it's a parallelogram. If both pairs of opposite angles are congruent, it's a parallelogram. And we have those different identifiers, okay? Yes?
On the GeoAlgebra, I just made like a triangle and it said it was a kite. The four of the points. This is not a kite.
Gotcha, yes. It registered it incorrectly because it was inverted. You made a concave shape, I should say. Okay?
Not a kite.
So let's go to this example real quick before we hop into our diagonals. Example 2 is still in our note packet. Let's find V, W, and Z. If we know angle A is 115 degrees, what kind of shape is this, guys? Isosceles trapezoid. How do we know it's an isosceles trapezoid?
Because the
Ask up.
lengths are congruent.
Yep.
The bases are parallel.
Very good, very good. Blessing, bless rains on after let's forget. Blessing, bless rains on after let's forget. Is that a third one?
Yeah.
Blessing, are you coughing, dude?
No,
Okay. All right. So set this correct. Pair of congruent sides that are going to be the legs. Pair of parallel sides, which are the bases. Isosceles trapezoid. So, what do we know about angle A and angle B? Angle A and angle B. What do we know about angles A and B? They're congruent because they're a pair of base angles. Why is Seth the only person answering anything?
Because he's talking louder.
Yeah,
It's not worth trying to talk
I was
over.
like,
Yeah.
we try answering above him.
he just blurts it.
Okay, let's go to raising your hand. Will that help?
Probably.
Okay, let's go to raising your hand, okay? Seth, can you do that too? Okay. So, if we know those are pair of congruent base angles, what does that tell us about one of our measures? Raise your hand. Kenny. They're congruent. So what do we know about Z then, Kenny?
Equals 115.
Very good. Z is 115. So Z is 115. That's one of our answers.
Degrees.
So actually, we don't have to put degrees here because Z already has degrees on it. So you can just put 115 there. Now here when I write it, I should put degrees because it's talking about the angle. But if you want to be better safe than sorry, you can always put degrees. And I'm not going to count it wrong, really.
What if we, like, it doesn't need the label, but we label it anyway?
That's actually what I just said. And it would be fine. I'd be okay with it.
I mean, like, okay, so it just does, we label the side length as like a degrees and stuff.
Oh, that would be incorrect. Yeah. All right. Is there any way we could find another angle here? Elizabeth. I love it. W plus 18 plus 115 equals 180. Elizabeth or somebody else, give me the reasoning behind why that works. Okay, Dylan, go ahead.
Because they're leg angles.
Because they're a pair of leg angles, and leg angles are not congruent.
Or,
Supplementary, adding up to 180.
I want to say 7.
So, W plus 18 plus 115, that's 133, equals 180. Subtract 133, we're just doing an algebra equation at this point. Geometry just tells you how to set up the algebra equation.
I know, why aren't we getting paid?
Wish we were.
Because they can't afford it.
I understand.
Because we're getting paid to set up our own homework, too.
Yes. W is 47.
I mean, we have to. We should be getting paid.
Does that mean that angle's 47? No.
No, it's just what you plug in for.
Yeah, it's what you plug in now. Do we have to find that angle?
No, but if you want to find B, you should.
Okay, if you want to find V, that would be one way to find it. That could be one way to find it, because what should we know, raise your hand, about angles D and C? Kenny.
Just supplementary.
Angles D and C should not be supplementary.
They're
No.
supplementary.
Let's go to Dylan.
They're congruent.
They're congruent. Why do we know they're congruent?
Because it's an isosceles.
An isosceles trapezoid, and they're a pair of
Base.
base angles. Now, they're not necessarily congruent to the other one, are they? So if we find the angle D, do we know the angle C?
Because Z is the same as.
If we find angle D, do we know angle C? Yes, because they are congruent. Is there an alternative way to find angle C if we wanted to as well?
Yes.
How would we find angle C the alternative way, Elizabeth? Yeah, we would take 115 plus V equals 180 because angles B and C are what? A pair of?
Supplementary.
A pair of supplementary angles because they are a pair of? Because they are a pair of? Leg angles.
Langles.
Okay? And so we can go about this either way. We've already kind of started to dive into the base angles of the bottom, so let's go ahead and do that. 47 plus 18 would make angle D, 65 degrees. So what does angle V have to be then? Or excuse me, what does measure of V have to be?
65.
65. So those are our three answers. Any questions on that? Now, was any of the math part, solving equations, was any of the equation part very, very difficult necessarily for us?
No.
Compared to what we've done, not really. No, I'm not saying that's the easiest thing. I'm not saying you can't struggle with that. I'm just saying compared to other things we've done, I would say that's not one of the harder things we've done. Would you guys agree? Okay. But knowing how to set things up and knowing how things relate to each other, that's what's new to us. Okay? That's what we have to focus on. Continuing on. The diagonals. They're congruent. Diagonals are congruent. Okay. That should finish off the note card as we go back to the note packet. A trapezoid is isosceles if and only if its diagonals are congruent. So all isosceles trapezoids, the diagonals will be congruent. If in a trapezoid the diagonals are congruent, we automatically know it is a trapezoid as well. So here we see a trapezoid with diagonals. If D to B is congruent to A to C, if those diagonals are congruent, then we know it's isosceles, even if it's not marked that it's isosceles. The diagonals are being congruent is enough to tell us it's isosceles. That's what this theorem says. Does that make sense? Cool beans. Anyone still need this? Alrighty. Let's go to an example problem then if we flip the note packet page. You do. Raccoon eyes. Okay. How could we go about finding x if we know, which I haven't told you yet, if we know this is an isosceles trapezoid? So now we know. The more you know. Reading rainbow?
No, the morning girl.
It's the reading rainbow.
No. Like, no. Yeah.
The reading rainbow.
No, not the reading rainbow. It's a different show.
Kenny, we can settle it later. Put it away. Thank you. Okay. How can we find x here? What can we do with the diagonals here in this isosceles trapezoid? What do we know about the diagonals? What do we know about the diagonals in isosceles trapezoid? What do we literally just learn? They're congruent. So, do we know what either diagonal really is, measure-wise? No. Could we write what it is, though, like in an expression?
I guess, yeah.
Okay, what would I say the diagonal A to C is? No, I didn't say the diagonal's cut in half. They're congruent. So how would I say, what's the length of A to C?
That would be 10 plus 3x minus 4.
Very good. 10 plus 3x minus 4, correct?
Yes.
That'd be the measure of A to C. Okay, well, what would the measure of B to D be? X plus 12 plus 8. Now, raise your hand on this one. If we know those are the two measures, and we know the two measures have to be what compared to each other? The same. So we set them equal. Okay, so raise your hand to tell me the equation here. Elizabeth?
3x minus 4
Not quite. Not 3x minus 4 equals 10. 3x minus 4 equals 10 would be saying that A to C is cut in half. That's not what's happening here.
Oh, wait, no.
You got it now?
Yeah.
Okay, let's try it again.
Okay. 3x minus 4 plus 10 equals x plus 12 plus 8.
There you go. 3x minus 4 plus 10 is equal to x plus 12 plus 8. We set those two diagonals equal to each other. Is this going to be the most complex equation ever? Probably not. Go ahead and solve it. So, we combine like terms that you want. 3x plus 6 is equal to x plus 20. From there, I would subtract x. 2x plus 6 is equal to 20. Subtract 6. 2x is 14. Divide by 2. X is 7. Landon did this, but do we have to plug it back in to find if make sure they're equal? No, but you can. So what you do is you get 3 times 7, which is anyone, minus 4. So this bottom part is 17. X plus 12, 7 plus 12 is going to be 19. Wait, 19 and 17, those aren't the same. Is that an issue?
No.
No, because we don't have the full diagonal yet, though. The full diagonal, A to C here, the measure of that
27.
would be 10 plus 17, 27. The measure of D to B would be 19 plus 8, which is also 27. So does it work out like it should? Yeah. Okay, let's continue on. Mid-segment of a triangle. This is a throwback, okay? Not even Thursday and we get a throwback. How neat. Okay? Say this is a triangle. D is the midpoint of segment A to B. So we know A to D and D to B are congruent, right? That's what midpoint would mean, right? It's in the middle, okay? And we know E is the midpoint of segment A to C. So we know A to E is congruent to E to C. It doesn't tell us that A to D is congruent to A to E. It doesn't tell us that D to B is congruent to E to C either, okay?
Parallel.
Now, what is the length of mid-segment D to E? Now, Seth, you mentioned parallel. What is parallel here?
B to C and D to E.
Very good. Those are parallel. That's part of our triangle mid-segment theorem from before. They're parallel. And then what do we also know about the length of D to E, raise your hand, compared to B to C? What do we know about the length of D to E, the mid-segment, compared to the length of B to C, the third side that is parallel to? Okay, Seth?
It's half.
It's half. So the measurement of segment D to E is not 16. Nope. Half of 38. 19.
I was close. And I didn't even use my.
Okay, so what are you going to do if your boss tells you, hey, we have 38, I don't know, we have 38 panels of fencing we need, and 1 gallon of paint will cover 2 panels of fence. How many go grab enough paint for this? Or let's say you're doing your own company, you figure that out. 38 divided by 2, 19. 19 gallons of paint. There's practical uses for these math facts as well, right?
No.
Okay, you're right. Math is only ever used by math teachers, and that's it.
Yes.
Yeah, totally not true.
Only accountants and
Okay.
every other daily thing that we use.
I got an $800 calculator for this.
Nice. All right. Mid-segment of a triangle, once again. The mid-segment's half the length of the third side, and it's parallel. Okay, that's a throwback. We've learned that before. Mid-segment of a trapezoid is going to be somewhat similar. So let's say we have this trapezoid here. The bases are parallel, okay? So we have a base up at the top. We have a base at the bottom. We have a leg on the left. We have a leg on the right. Now, do we know these legs are congruent to each other? No. They could be, but we don't know. They look like they're probably not.
What about that middle?
Now, oh, that middle one. It looks like it cuts it in what? Half. We can know it's half because over here on this left leg, we see 2 congruent parts, right? So we know that this over here, this point that I just marked in yellow, is a midpoint, correct? Do you know the same thing about the point on the right-hand side as well of the leg? Yeah, because it cuts that leg in half too, most noticed by those tick marks. So this would be a mid-segment, wouldn't it?
Yeah.
So that'd be a mid-segment. Now, the mid-segment theorem for trapezoids, okay, we have the mid-segment theorem for triangles, right? It said for triangles, recap, triangles, okay? Nice. Parallel to the third side, half the length, right? Okay? Parallel to each base, so it's parallel to both these sides. Does that make sense that it'd be parallel to both sides, right? If it's parallel to one, it's going to be parallel to both here. So we see that written there with the arrow. And its length is 1/2. Are we seeing a half again? Half length. Okay? But in this case, how would we choose which base it's half of, right? Because there's 2 sides here it's parallel to. So you can't just go half of one of them and just randomly choose. That wouldn't be consistent. So you do half of the sum of the bases. So what you do mathematically here is you take your first base, base 1, then you take your second base, base 2. Kind of looks like basil. Base 1. Plus base 2. And divide by 2. That's going to give you your mid-segment. So it's a very similar idea to the mid-segment of a triangle. Does that make sense? How it's very similar?
Trapezoids are just triangles that got haircuts.
Okay. That's actually really funny, I'm not going to lie. All right. Once again, with a triangle mid-segment, well, I'll get to you in 1 second, Elizabeth, thank you. In a triangle mid-segment, parallel to the third side, half the length. Trapezoid mid-segment, parallel to both bases, so both those sides, the third and fourth sides, and half the sum of the length, because there's 2 sides now. There's 2 sides, so you have to add them together first, then you cut in half. Elizabeth.
So, what if on a problem you're giving the mid-segment in one of the bases? Would you just do the base on top and the base segment on? No.
We'll do one of those problems actually here. So that question will be answered in a moment.
We should watch Flatland.
Hang on, but,
You'll need this?
yeah, I was gonna move the equation number because it was too close to
Okay.
We
Maybe-
should watch Flatland in here. You ever seen it? It's a movie.
Oh yeah,
Oh, yeah.
I remember it.
Yeah,
I texted Mr. Wallace. It's pretty cool.
It's a math.
He texted back.
It's a math.
about shape.
Yeah. Or geometry, not math.
Find x. So this is a trapezoid. What do we know about this in the middle?
It's half the sum.
Mid-segment.
It's a mid-segment. How do we know it's a mid-segment? We're not told it's a mid-segment.
The middle.
How do we know it's in the middle definitively?
2 legs or
The legs are marked, aren't they? Okay, so we know for a fact it's a midsegment. You have to know for a fact, which we do. So could somebody help me set up my equation here? Okay, Elizabeth, go ahead.
18 plus 48 over 2.
Very good, very good. 18 plus 48 over 2 is going to equal our x. Okay, now, doesn't matter which base we call base 1 and which base we call base 2. No, it's very arbitrary. Okay, there's no consistent rule for it, because otherwise, if the trapezoid's rotated, then it's all thrown off anyway. And realistically, do we need to know the order if we're just going to be adding them anyway? No, because you can add in any order. Questions on the setup? Okay. So what's 18 plus 48? 66. Divided by 2, so x is 33.
Ooh, so close to 22.
Not anywhere.
All right. I guess it could be the next, double number. But anyway, I think that's what you meant. Question on that? All right, let's roll into an example that does answer Elizabeth's question here. Here we're given a base. We don't know the other base. It's x. And what else are we given? Midsegment. Once again, how do we know it's a midsegment?
Because the two sides are congruent.
The legs are marked. The legs are marked that, hey, this leg was cut in half. 2 tick marks, 2 tick marks. This leg was cut in half. One tick mark, 1 tick mark. It is definitively a midsegment. So, can we set this one up exactly the same as our last one? No, but it can be very similar.
If you just take 15 times 2.
Kenny.
It'd be 22 plus x equals, divide by 2 equals 15.
Very good, very good. Kenny just repurposed our equation. Kenny just said, hey, our equation is base 1, b1 plus b2, if you will, divided by 2 is equal to the midsegment. And he just plugged in what we knew. He said, hey, we know one of the bases is 22. So you're supposed to be proud. The other base is x. We just call it x. Divided by 2 stays equals the midsegment. Oh, we know it's 15. Repurpose these equations. Repurpose them for what you know. To solve this equation, what do we do with that divided by 2? Do what on both sides? Multiply on both sides by 2, or 2 over 1 if you prefer to call it that. The 2 and 2 on the left-hand side reduce, so we're left with 22 plus x. What does the 15 and the 2 do?
30.
Multiply to 30. So now what's our one step left?
Subtract by 22 from both
Subtract by 22 on both sides. I love the both sides part. So x is 8. Is it reasonable that our other base would be less than 22 and less than our midsegment? Yeah, that's reasonable to say. Because our midsegment is less than this, right? So it's reasonable to say that. Okay? Just like on our previous problem, is it reasonable to say that our midsegment is halfway, or is exactly actually halfway between 18 and 48? Yeah, it's reasonable to say it's going to be between the two. Okay? Let's go to the Kite Notecard.
Thank you.
Note card. What else is it? It's nothing else. It's its own in its own category.
It's special.
It is special. Relationship of sides. 2 pairs of consecutive sides are congruent. 2 pairs of consecutive sides are congruent. Slopes, no relationship. No parallel sides here. Parallelograms, both pairs of parallel sides. Trapezoid, exactly 1 pair of parallel sides. Kite, no parallel sides. Relationship of angles. 1 pair of opposite angles are congruent. 1 pair of opposite angles are congruent in exactly 1 pair. Let's use our note packet to help with that. We have a kite here. So, this kite, let's go with the definition actually. Sorry, the definition. A quadrilateral that has 2 pairs of consecutive congruent sides. So, 2 pairs of consecutive congruent sides. So over here on the left-hand side, these 2 sides are consecutive, they're next to each other, and they're congruent. Or on the right-hand side, these 2 sides are consecutive with each other, and they're congruent. But opposite sides are not congruent. Are opposite sides congruent here? No. If it was, it'd be a parallelogram, but it's not a parallelogram. Can't be a parallelogram because the kite cannot be having any parallel sides.
So there's other sides.
Okay. Let's talk about the angles here. This is in your note packet. The pair of congruent angles, I said one pair of opposite angles are congruent. They're going to be between the consecutive sides that are not congruent. So these consecutive sides are congruent, A to B, B to C. These consecutive sides are congruent, A to D, D to B, D to C, excuse me. So between those pairs, angle A and angle C are congruent. So it's always going to be the angles that are between the non-congruent sides. Okay? So there's going to be something congruent everywhere you look. Here, two sides in a row. Here, two sides in a row. Now, when the two sides aren't congruent in a row, we have the congruent angles. Okay, does that make sense? Okay, that's in your note packet. You can draw those congruent angles in there in your note packet, by the way. Okay? So let's do example 6, knowing this about the angles. So, given that we have kite ABCD, find the measure of segment A to B, find angle B, and find angle D. Well, how could we find the measure of segment A to B? Knowing it's a kite. Yeah, Landon.
Segment A and D are congruent to segment A and D.
That's exactly correct. Those are consecutive congruent sides, okay? Now, we know it has to be this side instead of the other because not only does it look like it, but there's non-congruent angles there. So that has to be the congruent sides. So A to B is 7 centimeters. What do we know about angles B and D in this problem? They're congruent. They're the congruent angles. Okay, do we know what they are yet? No, okay, so we can call DX and we can call BX. Now, what do we know about this shape and some of the angles of this shape? 360. How do we know the sum of these four angles is going to be 360?
I would say so.
55 and 105.
That won't be the reason. What kind of shape is this broader than kite? Quadrilateral.
Circle.
Four-sided figure. If it's a four-sided figure, all quadrilaterals have an internal angle sum of 360, just like rectangles or squares or parallelograms or rhombi or trapezoids. Or isosceles trapezoids, not a sphere. Nope. Sphere is 360 degrees round, not angles. There are no angles in a sphere, okay? Now, so what we can do is we can add up 55 plus 105 plus x is equal to 360. Mr. Costle, what if I don't remember what if I don't remember the internal sum of a quadrilateral? Great question. N minus 2 times 180 will work. You can always use that to find the internal sum. 4 minus 2 is 2. 2 times 180, 360. So we solve this equation. 55 plus 105 is 160. Plus x is 2x is equal to 360. Subtract the 160. 2x is 200.
That's a big angle.
Divided by 2. X is 100. So what's the measure of angle B and what's the measure of angle D? 100 degrees each.
He's got a tax on.
Yeah, it's called his brain is a calculator.
Quality went to college.
Not he's a math teacher. His brain is a calculator.
You're gonna be smart.
That is true.
Look at all electricians.
Okay. Yeah, I know some electricians there. All right.
They go to trade school. That's
What's just the type? All right. Continuing on. Okay, I'll wait like 2 seconds.
It's what do they call that?
Alright, you're good.
It's a form of secondary school
Post-secondary
for
education.
that.
Yep. All right. Diagonals. Diagonals are perpendicular, meaning they form what kind of angle with each other? Meaning they form what kind of angle with each other if they're perpendicular? Right angle. And the diagonal connecting the congruent angles. The diagonal connecting the congruent angles. Which diagonal would that be here?
Oh.
A to C or B to D? Nope. Which diagonal is connecting congruent angles? Well, there's one pair of congruent angles.
C.
Nope. Oh, did you say A to C? Sorry. Yes, you're right then. A to C is connecting congruent angles because angle A and angle C here would be congruent. These are where our non-congruent sides are. So, in this case, say A to C, the diagonal is bisected. It's cut in half. You could draw that back up in that picture that we had earlier on our note packet as well.
I see like 4 triangles.
All right, continue on to our next example. Find the missing side lengths of this kite. Whew. That's a lot of different lengths.
Most of them are the same.
Okay. So, right here we know the diagonals, don't we? 20 and 12, this whole thing's 32. 12 and 12, this whole thing's 24. Aha. Now wait, what do we see 4 smaller versions of in this?
Triangle.
Triangles. Now what kind of triangles are these?
Right.
They're right triangles because the diagonals are perpendicular to each other. So these are 4 right triangles, aren't they?
No, they're left triangles.
So, could we use the Pythagorean theorem? Okay. Now also though, wait. In this triangle up in the top right-hand corner, X, U, Y, are these two sides congruent?
Yeah.
So what do we know about when the 2 legs of a right triangle are congruent? What kind of triangle is this? Isosceles, right? Which is also what kind of angles? 45, 45, 90. 45, 45, 90. Does anyone remember from last chapter how to go from the leg to the hypotenuse in a 45, 45, 90? Times by something. Square root of 2. So what's 12 times the square root of 2? 12 times the square root of 2. Is that going to be the same case for y to z? Yeah, it will be. 12 times square root of 2. So see, these 45, 45, 90s, they're still useful here. Now, if you don't know that, could you use the Pythagorean theorem?
Yeah,
Sure, that's what we did when we learned it in the first place, right? Was we did the Pythagorean theorem a bunch with some of those problems, and we said, oh, there's a pattern. Okay, now, with the other ones, w to x and y to z and w to z, we're going to have to use the Pythagorean theorem. So, here, the Pythagorean theorem, how could we set this one up? It's not a 3690. How do we set up the Pythagorean theorem on the triangles on the left-hand side? They're both the same triangles, 20 and 12, 20 and 12. Elizabeth.
Would it be? Never mind. I don't know.
Kenny?
12 squared plus 20 squared equals c squared.
Very good, very good, very good. C squared, our hypotenuse one we don't know. Square the 2 legs in no particular order and add them together. 12 squared is 144. 20 squared is 400. Is equal to c squared. 144 plus 400, 544, is equal to c squared. Last I checked, that's not a perfect square, but we do square root it, and I'm okay with a decimal this one time. C is approximately 23.3. Thank you. So we had to use the fact that these are all a bunch of triangles and all a bunch of right triangles so we could find different side lengths, correct?
Yes, sir, Mr. Consul, sir.
Does that mean you could go the reverse way by knowing these to find the triangles inside as well? Yeah, if we can go one way in math, we can always go the other.
I hope so.
Okay, right, right, right.
Left.
Left. Nice.
Theoretically, anyway.
All right. All left.
Mr. Consul.
What's up?
So in Rossi, we're learning land navigation. We actually, in the last, Friday.
It is pretty funny. So don't do number 24, haha. But still do the funniest one.